I think it might be worth it for me to extend this line up a little bit. Do you all see the region? Yeah? It's the one that's bounded by all of them. So it's this region right in here. It's this thing right in here. We want the area of that thing right there, don't we? That's what we want. Now I shaded it in all dark, so it's kind of messing it up, but would you like to use vertical rectangles or horizontal? And why? Vertical, okay. Or horizontal. Okay, yeah, so look, if we do horizontal, this is all just in my way. If we do horizontal, then if I draw this right here, the green's on the right, blue's on the left, right? And then it's going to change at some point, like in here, we're going to have this one and this one, right? And then it's going to change again. You would have to do 3 different integrals, but it could be done, couldn't it? You could break that up into 3 separate integrals with horizontal rectangles. Not a fan, all right? Because if I do vertical, what happens? It's just one thing, right? If I draw a vertical rectangle in there, no matter where I draw it, which one's the top one? Red one's on top, bottom one's the blue one, right? No matter what. So as I move all the way through, I've got the same upper and lower functions. What about how far I'm moving left and right? What's my left side? What's my lower limit of integration? Pi over 2. What's my upper limit of integration? Pi. Awesome. I'm in business. You don't even need an intersection for this one. Now, had you done the other way with 3 different integrals, you would have to find that intersection, and that intersection. So help me out here. Integral, pi over 2 to pi. Top one, x minus bottom one, sine x. Done? Dx. There we go. I think that's a pretty clean integration. Would you agree? Antiderivative is 1/2 x squared plus cosine x. Evaluation bar, pi over 2 to pi. Your answer is going to be kind of weird here, but it's okay. Pi goes in first, right here. So won't we just get 1/2 pi squared? Right? What's cosine of pi? -1. Now we plug in pi over 2. So be careful here. Pi over 2, what's pi over 2 squared? Pi squared over 4 times 1/2. Pi squared over 8. So I'm going to write as 1/8 pi squared. Now plug in pi over 2 into cosine. Cosine of pi over 2 is 0. Collect some like terms together here. I'm going to 1/2 pi squared minus 1/8 pi squared minus 1. And then, so I just moved that one out there. Move the one in the back, 0's gone. What's 1/2 pi squared minus 1/8 pi squared? What's 1/2 minus 1/8? 3/8. So 3/8 pi squared minus 1. So up to this point, we've been getting pretty good, nice little answers, right? Like 10/3, and then last one was a little weird, but this one's got pi in it, so this area is actually an irrational number. It's can't be approximated easily. All right. You don't want to do it the other way, right? Vertically, or with the horizontal? No. Yeah. I don't either. There's the region. My other class also, we talked about something briefly. We were just kind of interested in this. I don't know why we got onto this, but we were just talking about if you take the sine curve and you draw y equals x, which is the diagonal, where do they hit each other? Just out of curiosity. And what it comes down to is setting them equal to each other. Where does sine x equal x? And that can't be solved. There's no algebraic technique to solve that. So you can't like take arc sine on both sides or anything like that. What happens if you do that? Try like arc sine here, arc sine of sine, go away, you get x, right? Arc sine here, you get arc sine x. So now you're trying to solve for x, but it's still in terms of x. You can't release that unless you hit it with sine. So it's the x cannot be isolated. There's no way to do it. So anyone know how we could do it though? Not algebraically, but Wolfram alpha, I'm sure would do it.
Get closer and closer on both sides.
Okay, you could do something in Cal 1. I know I talked to my students about it, but it's just a brief thing. Newton's method? That's the way we would solve that equation. We'd use Newton's method. But we're not going to mess with it. Next one. Where are we at? 4? Sketch the region bounded by x equals y to the 4th. Hey, look at that. That's x equals, not y equals, x equals. So I'm already thinking horizontal rectangles because they're both solved for x, right? X equals root 2 minus y, and then y is greater than or equal to 0. Okay. What the heck? All right. What's x equals y to the 4th look like?
It's higher than the fourth. Oh no.
Parabola, but not this way, right? Sideways. Now, again, my other class, we had some issues here. So what I'm going to do is I'm going to make an old school t-table. X, y, right? That's an old school t-table. In this first equation, isn't our x always y to the 4th? So what I'm going to do is I'm going to start filling in this table, but I'm going to be feeding it y values and having it spit out x values. So I'll just start with some standard ones like -2, -1, 0, 1, and 2. So I'm going to just feed this thing right here some y's. So what's -2 to the 4th power? 16? What's -1 to the 4th? 1, 0 to the 4th, 1 to the 4th, 2 to the 4th, 16. So look at these now as ordered pairs, right? The x value is 16, so you go out 16, down 2, right? Yeah? Go out to the right 1, down 1. 0, 0. Go out 1, up 1. Go out 16, up 2. You basically get the real tight parabola opened up this way. All right, so I'm just going to kind of exaggerate it. Here it is. There it is. So this is x equals y to the 4th. How about that one? Well, it's a root function, right? So we know what root x looked like. It looked like half a parabola. So let's try this one. Let's do this one the same sort of way. Let's go x is equal to root 2 minus y, and let's plug in some y's. But we're going to run into some issues here because we have a root. We can't just plug in anything. We might have some problems. So give me some numbers that are going to be easy to evaluate in here. What?
Positive numbers?
Give me a number. Give me an example. I heard 2. What about 2 in here? What do I get? 0, so root 0, 0. 4, I can't do 4 in here because 2 minus 4 is negative, so that can't do negative roots.
Negative 1? Or 1? 2 minus 1?
6, I can't plug 6 in here. 2 minus 6 is negative 4. Square root of negative 4 is an imaginary number. You can do 1. What happens when you plug in 1? 2 minus 1 is 1. Root 1 is 1, so you get 1, 1. How about 0? You can plug in 0. Plug in 0, you're just going to get root 2. Give me another number. Negative 1. What happens if I plug in negative 1? 2 minus negative 1 is 2 plus 1, now root 3. Give me another one. Negative 2. How about negative 2? 2 take away negative 2 is 2 plus 2, that's 4. Root 4 is 2. So here we go. Now give me one more, but pick it, make it a clever one. Negative 6. Negative 6 in here would work. 2 minus negative 6 is 2 plus 6, that's 8, right? So if I plug in, what did we say, negative 6? That's, oh, hold on.
14, negative 14.
I don't want that. Not root 8, sorry.
Oh, sorry. Negative.
What would be a nice next perfect square? Negative 7. Negative 7. Then 2, take away negative 7, 2 plus 7, that's 9. Root 9 is 3. There. That's what I want. Okay, so this thing should be shaped like a square root function, but here are some points to help us graph it. 0, 2 is right here. 1, 1, I don't know, somewhere in here. Root 2, 0. 2, negative 2. I'm kind of eyeballing this now. 3, negative 7. I think I have enough. I think I see it. That's good enough. Do you see the region? Oh, wait, we're not done. Hold on, there's one more. Y is greater than or equal to 0. What does this mean?
Above the axis.
Everything above the x-axis. So here and up. So I'm not allowed to look down here. Do you see the region? Right there, right there, that little piece. So this may happen to you. And when this happens, I suggest you just redraw it now. Now you have a good idea of what you need, right? I'm going to just go ahead and do a new picture. I have this piece. I'm going to really kind of over-exaggerate. And then I have this piece like this. And I'm interested in this in here. This one is x is y to the 4th, and this one is x is root 2 minus y. How would you like to achieve the area there? Vertical or horizontal?
Horizontal.
Horizontal. Especially if these are functions of y. And they are, right? They're solved for x. So I have my rectangles in here like this. And as I move that rectangle up and down through this region, the right boundary and the left boundary never change. One more thing for us to determine. The points of where they hit. So I need to grab this point, and this one's obvious, right? 0. So I know my integral right now goes from 0 to something. So how am I going to figure out where those hit? Set them equal to each other, right? That means set this equal to this. Yeah. Set y to the 4th equal to square root 2 minus y. I don't remember doing this in my class earlier today. Why don't I remember doing this?
How would you solve that?
Huh?
How would you solve that?
Yeah, so how would you solve this? Oh yeah, you can square both sides.
You give
That's how we would try it. Let's see what happens. We're going to run into an issue. I know what we did in my other class now. I just don't remember doing it, but we didn't do this. Okay, if I square the left side, I get this, right? Square the right side, I get this. And that, unfortunately, is not a quadratic, so you don't have a method there. Again, this would require Newton's method, but sometimes you just take a shot at it. Like, just look at it. One? Y is 1? Works, doesn't it? 1 to the 8th equals 2 minus 1 is 1 works. Now, that may seem like, wait, that's cheating, but that actually does come up in the book on some of the problems. They don't expect for you to solve that equation. They actually expect for you to just try and just pick something and see what happens. Like, there should be a nice number. If it's going to happen, right? If they made this a 3, then it would be game over right now. But they make the problems like that intentionally.
I'm wondering why square root of 2 minus y could be y to the 4.
You were wondering what?
Doesn't seem right.
Yeah.
Square root of 2 minus y is y to the 4.
Yeah. Well, it works with 1, right? Okay. Any questions on that? We're going to do this just by inspection. Just by inspection. We're just going to say, we're going to go, y is 1. That is a formal process. This is a formal algebraic technique. Another way we might have gotten it is when I had the table up there earlier. I don't know if anyone wrote down when I put the table up here. Did we ever have the same point on both tables? Didn't we have 1, 1 on both tables? That would have given us our intersection point right there also, because the same point appeared on both tables. All right, I think I'm ready for the integral. I hope you are. This is 1. Where's my integral going to start? 0 goes from 0 to 1. And then I'm doing what? Yeah, the right boundary, right? Which is this one right here. This is a function of y. This one right here is another function g of y. All right. So the one on the right is this one. The one on the left is this one. So I'm going to have square root of 2 minus y minus y to the 4th dy. And then we get to integrate. I think I'll leave that integration to you. So I'm just going to say dot, dot, dot. And you may not like that, but on your test, when you get to the next exam, there will be just a few problems, maybe 1 or 2 in the beginning that are like this, where you actually have to work through the whole thing and get me the numerical answer. Like whatever, 10/3 or whatever. But then after those first few, everything from that point on is going to be set up the integral, but do not evaluate. So you'll basically get to this point, you'll box it, and you'll move on. So it's just a matter of can you generate the integral that you need to get the area? The actual computation of it, who cares? That's busy work, right? So that'll be our goal. So I'm going to stop here. I'll let you take care of that if you want on your own. All right. I was going to mention something else. Oh, yeah. So just out of curiosity, what would happen